Welcome. Ever wonder how engineers predict if a bridge will sway or collapse? It all comes down to second-order linear homogeneous differential equations. We are moving beyond just solving for x to mastering the language of stability. These equations allow us to model forces acting on a structure. By predicting these patterns, we can ensure safety and durability in everything we build. This is the standard form of our equation. It is the language we use to describe how a system changes over time. The components represent the fundamental states of a moving system. Y double prime is acceleration, Y prime is velocity, and Y is the current position. Think of this equation as a delicate balancing act. Each term pulls the system in a different way, and solving it means finding the exact path where these forces settle into a state of equilibrium. By adjusting the coefficients A, B, and C, we can model everything from a swinging pendulum to a skyscraper swaying in the wind. Our goal is simple yet profound. We want to find a specific function, y of t, that perfectly balances this equation to 0. We are not just solving a calculus problem, we are predicting the rhythm of a physical system. Whether it is a building swaying in the wind or a shock absorber in a car, we are finding the path it takes to reach stability. Remember, solving these equations is really about predicting the path of least resistance. It's how we ensure stability in the world around us. To solve these equations, we use a tool called the characteristic equation. It acts as a bridge, turning complex calculus into simple algebra. We assume a solution of the form y equals e to the power of r times t. When we plug this into our derivatives, the calculus naturally simplifies. Replacing derivatives with powers of r gives us the characteristic equation, ar squared plus br plus c equals 0. This algebraic form is much easier to manage, allowing us to find the roots that define the system's behavior. We have our characteristic equation. To find the roots, we turn to the trusty quadratic formula. The quadratic formula gives us the roots. Think of these as the gatekeepers of our system. They hold the secret to how it will behave over time. The characteristic equation holds the key to our system's behavior. But how do we unlock it? We look at the discriminant. The discriminant, denoted as d, is the part under the square root in the quadratic formula, b squared minus 4ac. This value acts as a personality gauge. It tells us if our system will decay without vibration, settle instantly, or oscillate rhythmically. A positive discriminant gives us two distinct real roots. 0 gives us a perfectly balanced repeated root, and a negative discriminant that reveals complex roots, where the system oscillates. By checking the sign of the discriminant, we can predict exactly how our system will behave before we even solve the equation. When the discriminant of our characteristic equation is positive, we obtain two distinct real roots, r1 and r2. This leads to our general solution, which is a sum of two exponential decay terms. This describes an overdamped state. Because the roots are real and distinct, the system returns to equilibrium without oscillating. It is heavily damped. When the discriminant of our characteristic equation equals 0, we find only one distinct root, which we call r. This creates a special case known as critically damped behavior. Because we only have one root, we multiply by time t to ensure we have two linearly independent solutions. This gives us the general solution, y equals c1 plus c2 times t, all multiplied by e to the power of rt. This represents the critically damped state. It is the absolute fastest way for a system to return to its equilibrium position without any oscillation or shaking. Think of a high-quality door closer. It doesn't slam and it doesn't bounce. It swings back to the frame as fast as physics allows. That is the power of repeated real roots. When our characteristic equation yields a repeated real root, r, we face a mathematical challenge. We need two linearly independent solutions to form a general solution. For repeated roots, the general solution takes this specific form, y equals c1 plus c2 times t, all multiplied by e to the power of rt. This extra t is crucial. Without multiplying by t, our two solutions would simply be the same, failing to span the necessary space. The T-term forces linear independence, creating the perfect structure for a rapid, critically damped settle. Remember this structure. It is the mathematical hallmark of a system that returns to equilibrium as fast as possible without oscillating. When the discriminant is less than 0, we encounter complex roots. These appear in the form alpha plus or minus I times beta. This represents an underdamped system. It is the heartbeat of physical oscillation, like a vibrating string or a skyscraper swaying in the wind. The system doesn't just stop. It oscillates back and forth, gradually settling over time. This is fundamental to understanding any mechanical or electrical resonance. When we encounter complex roots, our solution takes on a unique structure. The exponential term handles the dampening or growth of the system, while the trigonometric functions define the oscillation rhythm. This combination creates a wave that settles over time, a perfect model for vibrations in suspension systems or structural dampers. In 2026, the way we handle differential equations has fundamentally changed. We no longer spend our time on the tedious manual derivation of roots. Today, AI-assisted solvers handle the heavy lifting of the calculation. This allows engineers to focus on what actually matters, interpreting the results. The real skill is understanding how changing the damping or stiffness coefficients shifts the system. We move from solving equations to predicting physical stability. As we master this 2026 approach, we focus on interpreting the physical outcome. Remember, we aren't just calculating numbers, we are predicting the rhythm of the physical world. Consider our system equation. If we adjust the damping coefficient b, we change how the system settles. Here, with a low b, the system oscillates wildly. As we increase the damping b, the oscillations vanish. We reach critical damping, the fastest return to equilibrium. If b becomes too high, the system enters an overdamped state, becoming sluggish as it returns to 0. Modern engineers constantly tune this parameter to optimize performance, whether for bridge stability or automotive suspension. Consider a car suspension system. It's essentially a mass, a spring, and a damper acting together. The differential equation we've been studying is the mathematical blueprint for this physical setup. The coefficients b and c are our tuning knobs. Changing b, the damping coefficient, determines how quickly the suspension absorbs energy. Changing c, the stiffness, dictates how hard the spring pushes back. By adjusting these variables, we can control the bounce of the car. We aren't just doing math, we are literally tuning the physics of the environment to ensure a smooth ride. The core takeaway is this: these differential equations provide the predictive power we need to tune the physical world, turning complex vibrations into controlled stability. In structural engineering, skyscrapers use the math we've discussed to design tuned mass dampers. These massive pendulums are hidden at the top of buildings. The building's motion is governed by our differential equation. The stiffness constant C and damping B are carefully tuned so the building's natural frequency remains out of sync with external seismic or wind loads. By shifting these coefficients, engineers force the building to absorb energy rather than amplify it, literally using math to save lives during a storm or earthquake. In electric vehicle design, engineers must ensure that regenerative braking is smooth and comfortable for passengers. This is a classic application of the repeated roots model in differential equations. When we have repeated roots, the system is critically damped. It returns to equilibrium as fast as possible without any annoying oscillation or jerking. If the system were underdamped, the car would oscillate, causing a perceptible jerk for the driver. That is not the experience we want. By tuning the drivetrain to match the repeated roots solution, engineers create a seamless stop, maximizing energy capture while maintaining total comfort. Differential equations are no longer just static math problems. They are now core components of what we call digital twins. A digital twin is a dynamic virtual replica of a physical system. Sensors on the physical component feed live data, like vibrations or stress, directly into our differential equation. This allows the model to constantly recalibrate itself to match the actual health of the structure. By solving this in real time, the model can predict structural degradation before a failure actually occurs. It shifts engineering from reactive repairs to predictive maintenance. The core takeaway is that digital twins transform these equations from static design tools into live diagnostic systems that monitor our world. The most frequent error is mismanaging signs, especially with negative coefficients. A simple slip here transforms your entire physical model. If you accidentally add instead of subtract, your discriminant changes from 0 to something else, hiding a critically damped system. Follow these habits. Write out your coefficients clearly, use parentheses, and double-check your discriminant. It keeps your system stable and your math accurate. Now that we have solved for y, how do we know we are correct? We use the verification process. We plug our final solution back into the original differential equation. Consider this critically damped system. To verify our solution, we differentiate it once to find y prime and twice to find y double prime. After differentiating, we substitute these expressions back into the original equation. Every term must cancel out to reach 0. If the equation balances to 0, you have successfully modeled the path of stability. If it does not, double-check your derivatives. Remember, verifying is your safety net. Plugging your work back in guarantees your stability model is mathematically sound. The homogeneous equations we have mastered serve as our foundation. These deterministic models provide the stability and rhythm of the physical world. But nature isn't always smooth. In advanced fields like swarm robotics, we introduce noise, leading to stochastic differential equations. We aren't just predicting a path anymore, we are managing uncertainty. Imagine a swarm of robots coordinating in a complex environment. Each robot experiences tiny, random disturbances. Stochastic models allow us to account for this noise and keep the entire system on track. Remember, the math we've explored today is not just a classroom exercise. It is the core logic that will define how you design, analyze, and build the autonomous systems of the future. To wrap things up, remember that these equations describe the rhythm of the physical world. Your roots dictate the behavior. Distinct roots lead to pure decay or growth, repeated roots bring us to critical damping, and complex roots create the oscillations we see in everything from car suspensions to skyscrapers. Most importantly, remember, we aren't just calculating numbers. We are predicting the rhythm of the physical world. You now have the fundamental tools to analyze stability in any second-order linear system. Mastery over these oscillations allows you to design everything from safer buildings to more efficient electric vehicles. Keep practicing and keep predicting.